Okay, so this is another video of me working out my group homework. So I'm just going to make this really quick, just a little coordinate system. It says a perfect dipole P is situated at a distance z above an infinite grounded conducting plane. So the plane is kind of indicating it's three-dimensional. The dipole makes an angle theta with the perpendicular to the plane. Find the torque on P, the dipole. If the dipole is free to rotate, in what orientation will it come to rest? Okay, so let's see. First thing I'm going to do is just draw a little dipole here. And let's say that this side is positive and this side is negative. And then this is the angle of against the perpendicular, theta. Okay? So we have this conducting plane around the ground. And the hint is, it says use the method of images. So with this conducting plane, we're going to have I guess you could say, image dipole, right? Something like that, where the charges are going to be flipped. So over here we'll have our positive. Over here we'll have our negative. And we'll have our theta. Keep in mind, this is a distance z, right? Mentioned it's z above the plane. And this also is a distance z, because we're using our method of imaging. Okay, so I think that kind of sets up the problem. Now our torque, which they use n in the book, I don't know why, but they do, is equal to your dipole moment crossed with your electric field. Okay. Now the electric field of a dipole, which is what we're doing, this is essentially we're replacing that conducting plane with this bottom dipole moment. So the E field is just going to be, the E field that the actual dipole moment feels will be equivalent to if we just pretend there's this imaginary dipole, a distance z below. So this is an equation in the book. In fact, it is equation 3.101. And it says your dipole as a function of r and theta is your dipole moment divided by 4 pi epsilon naught r cubed times 2 cosine theta r hat plus sine theta, plus sine theta theta hat. Okay? Now in this particular case, our r is equal to just 2 times z. That's the distance from the imaginary dipole to the real dipole. So just plugging that in, we find that E of our dipole as a function of the r and theta is going to be P over 4 pi epsilon naught times, that'll be 1 over 8 z cubed. Just plugging that in. We have our 2 cosine theta r hat plus sine theta theta hat. Okay? And as for a dipole moment, if we were to draw this out here, let's say that this is the, this is our dipole P. And we'll actually do this one in, let's say, red, just as an example, minus, plus, it's a vector, so our vector is going to do, say, do something like that. And this is that angle theta. So we can find that our moment dipole moment is just going to be b cosine theta in the r hat direction. So that's this part, right? I guess you could call it, that's going to be your r hat direction. And then that's the direction of increasing radius. That's why that's the r hat. And then we're also going to get this sign, which I'm sure you can see, will be plus p sine theta. But notice that it's going in the increasing, as you move more to that right, towards the right, theta increases. So this is in the theta hat direction. Okay. Well, we have our E and we have our P. So if we want, we can find our torque. So our torque N is equal to the moment crossed with your E field. Now this is basically just a the cross product. So for that, we can essentially set up a determinant. P cosine theta. We have P sine theta. We have, so this is for our moment. And then over here, we have P over, so we'll take the R first. And keep in mind, we have A2, so that's going to be, or actually, we'll look at this one. So we're only going to take the R hat. So if we do the R hat component, that's going to be P over 16 pi epsilon naught z cubed cosine theta. And for the other one, there's not that 2. So you're going to get essentially the same thing, but instead of the 16, that 2 is not there to cancel it. So you'll get 32 pi epsilon naught z cubed. And then instead of sine or cosine, it'll be sine. And like I said, it's a 2 by 2 matrix. And you can do Cramer's rule to solve this determinant. So that's just multiply by this, then well, I guess if I were to do it right here, let's say you have A, B, C, D. The determinant of this is AD minus BC. That's essentially what we have. I think that makes more sense than just me randomly drawing lines. Okay, so there's that. So now all we have to do is go through and multiply this. So what do we get? We get P cosine theta. We actually get P squared cosine theta sine theta, all divided by 32 pi epsilon naught z cubed minus P squared cosine theta times sine theta, all over 16 pi epsilon naught z cubed. And I'm going to go ahead and just do a little bit of factoring here. So we can factor out a P squared cosine theta sine theta. And we can factor out a 16 pi epsilon naught z cubed. Right? And we'll be left with 1/2 minus 1. We'll go ahead and take the magnitude of this to get the magnitude of our torque. So even though this is 1/2, we're not going to worry about that negative. Okay, so let's see, we do that. And then also this is an identity. All right, that's an identity. So I'll just do it over here. Cosine theta times sine theta. I think it's actually 2 cosine theta sine theta is equal to sine 2 theta. So we can replace that and divide by the 2. So we're going to have minus 1/2, so we'll multiply by 2 from here, 1 from this one. And then if we divide this 2 over, so we're really multiplying by a 4. Okay? So you get p squared sine 2 theta divided by 64 pi epsilon naught z cubed. And this is the magnitude of our torque. Now, if we want to know how this thing is going to spin, well, we just have to remember the rules for torque. So if our torque is greater than 0, or our torque will be greater than 0, if theta is between 0 and pi over 2. If you were to plug, obviously if you had a unit circle, right? Let's just say that's the center. Sine is going to be positive from here. Oops. Sine is going to be positive along this side, right? Which is 0 to pi, but do keep in mind we have the 2 in here. Okay? And when we have a positive torque, it rotates counterclockwise. Now, n is less than 0. Well, that's going to happen if we think of the unit circle on this side. Again, we have to keep in mind that there's already a 2 in there, so that'll be pi over 2, between pi over 2 and pi. And when we have a negative torque, it's going to rotate clockwise. So hopefully that makes sense for the most part. That's kind of our idea here. So hopefully that makes, for the most part, sense. Again, we use our equation here, P cross E. We have an equation for E. I can find our P. We basically just do the cross product. There's a trig identity, and then just recognizing when this is, when our torque is positive and when it's negative based on the angle. And that's basically it.